convolutional neural networks. And the whole concept of convolutional neural networks is derived from the fact that I would like to combine learning of both a classifier and representation. And that makes the concept of learning deep. Deep because I would like to also learn how to represent raw data. And I covered a few components of this convolutional neural network so far. So we were talking about convolution and convolutional layers. So these were building blocks for this representation learning. I told you about pooling, which is one of the ideas that can be used for reducing resolution of analysis. I told you about flattening, and I presented you a general structure of a convolutional neural network. So this general structure is we begin with a module or a block that is concerned with representation derivation. So these are these convolutional modules. So there will be most likely many convolutional layers here, and there will be many pooling layers, and this ends up with a flattening of the last layer outputs. And the second module that we have is a fully connected classifier or a dense network. This fully connected network or dense network. So let's name it. These are convolutional layers. Convolutional layers plus pooling, obviously. And here is a multiple layer perceptron or multiple layer feed-forward neural network or dense network. And what we are talking about at the end of our last meeting, we were talking about a loss that is being used commonly in data classification in convolutional neural networks. And this loss was a categorical cross entropy. And this categorical cross entropy, the general formulation for that was that it was an expression that involves, it's a general formulation. So if we have I outputs, then Pi are probabilities of true categories or targets. Qi are actual values produced at the end of the network. And since we are considering a mutually exclusive case, classification cases, so our target vector basically is a one hot vector. So it just has a single one. So that categorical cross entropy for classification problems where only a single class is supposed to win just reduces, and I have shown you to the expression that is very simple. It is just a minus log of probability that is generated at a target output. So the loss basically involves generation by a network of probabilities. So if I would like to compute a loss and I have, let's say, P classes, then what I have to produce, I have to produce P values that are probabilities. If you look at this fully connected layer, this is a multiple layer perceptron. what we are producing there are not probabilities, or just some real numbers. Depending on the adopted nonlinearity, these real numbers can reside in different intervals. So if I would like to apply loss that is based on probabilistic description of the network performance, I need to place here one more module, so that outputs, which are, so here are, let's name it some outputs of this fully connected layer. So let's say that there are P outputs, and what I need to do is I need to introduce a block that converts them to probabilities, if I would like to use a categorical cross-entropy loss. So how to implement this block? I need to somehow propose a layer or a module that is going to produce probabilities based on some real input, a vector of real inputs. How to do that? Well, it can be done in many different ways, because what are probabilities? If you would like to define the basic requirements that a vector of values needs to satisfy to treat this vector as a probability distribution, there are very simple and very basic requirements. So each value of this vector obviously needs to be a real number that is bound within an interval from 0 through 1. So that's the first requirement. Well, and the second requirement is a requirement that all these values need to sum up to 1. And basically that's it. So any transformation that will transform y's into q's. So any transformation, these are q's, and this q vector needs to be transformed, the y vector needs to be transformed to a q vector. Any transformation that provides that these two requirements are satisfied is fine. And as I said, there are many possible choices. And what particular choice or what particular method has been adopted for training of convolutional neural networks? The choice is not at the first sight obvious at all, because the idea that is being implemented is the following. This transformation is a transformation that basically from 1 through p e to the power y sub j. So this is the transformation. The transformation is looks a little bit weird. It has a name that probably many of you have already heard, and this is called the softmax transformation. So if I would like to tell what is a value of Q5, what I need to do is I need to compute the following expression, where here I will have a sum over j. J is from the first output to the last output, and in the numerator I have just e raised to a power of y5. And it looks weird. And this is not the most straightforward solution for converting outputs to probabilities, but it has a very, very nice property, and this is why it has been adopted. So before I proceed, just observe that this formulation satisfies my constraints because y can be any number from minus infinity to plus infinity. There is no any restriction for that. Observe that if y goes to minus infinity, qi tends to 0. If y goes to plus infinity, then qi will go to 1 because numerator will never be greater than the denominator. And also it is trivial to check that if you sum up these qi's, you will get 1. So this expression, this idea, satisfies constraints because I have these two constraints that needs to be satisfied, and they are satisfied. So the output of this block are probability, can be treated as probabilities. And why this has been chosen over several other alternatives? Because what could be other alternative? Other alternative could be, for example, qi could be yi, for example, squared over sum of yj squares, and so forth. So there is an infinite amount of different concepts, but none of them has been selected but this one. So where is the advantage of this softmax formulation or of this transformation? The advantage is closely related to our objective of minimizing the loss. Because what is a loss? Once again, a loss that we have is a minus logarithm of qi. This is our loss. And if I have a structure, so let's assume that I have my, here is my output generated from my deep neural CNN classifier, and here is this softmax layer, and here are the fully connected layers. So there will be fully connected layers, and then there will be convolutional layers and so forth. So if I would like to make any change to a weight, either here or there, any weight, basically, as you recall, an update of a weight can always be expressed as a delta rule. And this delta rule just requires that this is a weight that corresponds to some, for example, neuron I, and this is some kth parameter of this neuron, will be proportional to the error that is being projected onto the output of this neuron, and components that are related to the input. So basically, to be more specific, is a derivative of activation for this particular neuron, I. So this is a neuron I, and times input at this weight. Let's name it xk. Just it doesn't obviously it is not x means x is here. X is something that comes here, and I will typically name it y because it will be the output of the preceding layer. But let's call it x. So and basically this part, I can say that this is equivalent to a derivative of a loss with respect to the output. Now, I'm making equality between these two notions. I can treat it as an error just to make it look appropriate for a delta rule. But in fact, this is a derivative of the loss with respect to the output of this particular neuron. So if I would like to compute these derivatives or these errors, what I need to do is I need to make these projections of an error or of the computing these derivatives, starting from our last layer. So if I am interested, if my weight is a weight that, and now I will put S, maybe not S, but that's wrong. So let's assume that this is some layer. The last layer of my fully connected network is K. So this is a kth. I have K layer fully connected or dense network at the last module of my convolutional network. So let's assume that this is a layer, this is a weight that belongs to somewhere to this layer. So if I would like to make a correction to this weight, what I will need to compute is I will need to compute a derivative of a loss, and this is a weight I K. Now I changed notation, and K I see is not very fortunate name, so let's make it M, and also here let's make it M. It's just an index, but I don't want to confuse. So what I will need to compute is I will need to compute what is a derivative of a loss function with respect to this particular. So this is this particular output. This is some output. This is some y. This is some y I. And it goes here. Maybe it's not the last line. Sorry for being not very. So let's it's somewhere here. This is my yi, and it gets converted to this qi. It gets converted to this qi. I need to compute this derivative. So what is this derivative? What is loss? Loss is here. It is a logarithm of my output probability. And now how probability is related to outputs of my mth layer of a fully connected network. Well, they are related using this softmax. So I can say that qi is e to the power yi divided over the sum over j for all inputs data elements. So e to the power yj. So let's compute this derivative. What is dl with respect to the yi? This is a derivative with respect to dyi of minus log and qi. So what I have is I have a logarithm of this. A logarithm of this expression is just a difference of two logarithms. So minus logarithm of qi is just a minus, and here I have a logarithm e to the power yi minus a logarithm, and here is a sum, and so forth. So if I make a simplification of that, what I have is I have minus yi plus, and there will be a logarithm of this sum. And now I would like to differentiate this with respect to my yi. This is something that I need to compute right now. I need to differentiate with this, with respect to this. So if I am computing a derivative of loss with respect to dy, a derivative is -1, because a derivative here with respect to yi is just 1, and plus, and I have a derivative of a logarithm of a sum. So a derivative of a logarithm is 1 over the value that is under a logarithm. So this will be 1 over, and here will be a sum e to the yj from j equal 1 through p. And now I have still, I need to apply a chain rule, because this sum, if I would like to write it explicitly, will be e to the power y1 plus, there will be somewhere here yi, and there will be somewhere here, e to the power yp. So the only element that contains yi is in this element of a sum. So basically, it will be, and this is a derivative of e to the power of x is e to the power of x. So this will be e to the power yi. And if you look at the definition of a softmax, it is just -1 plus qi, because the second term is just a softmax. It is just a qi. So if you look at that, you will see that my particular choice of a loss function enables to get a very simple form of a derivative of a loss with respect to the input to this softmax module, which is the output of the last layer of neurons in a multiple layer perceptron. One more thing, if I would like to compute what will be a derivative with respect to any other neuron, because this is our softmax layer. This is our softmax layer. So what I have here is, for example, I have this output I. This is my qi, and this is my input. This is yi. But obviously, there is somewhere else, there is a yj, and here is my qj. So I have many outputs, many inputs. This is a softmax layer. So I already know what is a derivative if I will be backpropagating an error. If I will be backpropagating an error through this line where the winning output is located. But how about propagating the error on any other output? Because I will be propagating this error or computing these derivatives not only for this particular one output, but for all lines or for all neurons that are in my network. So what is the value of this derivative here? Well, a derivative is also very simple to compute, because you see that that's my loss function, and the first term does not depend on yi, so it just is not present. So the only thing that here remains is just qj. So just to conclude, a derivative of loss with respect to yj is qj, and the derivative of loss with respect to yi is -1 plus qi. And what we are doing is, if I would like to, what I'm going to do is I am to minimize my loss. If I am going to minimize my loss, a general formula will always be that if I want to change any parameter in the network that is located anywhere in the network, I will be trying to make a step that is in an opposite direction. So what is what I would like to notice here or to show is this minus sign. So when I will be producing errors that get propagated, because the most important element in neural network theory is how to update weights. And I will have a structure where I will have softmax. So this is my softmax. Then there will be this multiple layer perceptron. There will be this multiple layer perceptron. And this is last layer of this multiple layer perceptron. And this is the first layer of this multiple layer perceptron. So this is a dense part of my network. And then comes convolutional parts of my network. So I will be having, this time I will be having three-dimensional modules or structures. Just for the sake of clarity, let's say that in this convolutional networks, I will just write some part of this two-dimensional structure, and there will be so I don't want to play in I'm not very good in 3D drawing. So anyway, this is this convolutional part of my network. And learning, what is learning? Learning is to compute a loss. So I compute a loss, and what I need to do is I need to project this loss at every output in every layer. And what I am doing, so in every output, in every layer, every dot is just a projected loss or a derivative of a loss with respect to this particular output. And if I would like to make these computations, what will be the losses? If this is this output number I of the last layer of my fully connected network, we can see that a derivative is -1 plus qi, and since I need to apply this minus sign here, it will be just 1 minus qi. This is the error. I can write here. This is an error delta I. Whereas everywhere else, every other neuron here in this layer will have an error which is just qj, and this is a loss for a neuron delta j. So once I am done with this step, I can say that my output neurons of my fully connected layer have identified errors. What errors are performed for these neurons? And then these errors are just then back projected using a BP algorithm through all the layers of my multiple layer perceptron. And exactly the same happens when I am back projecting neurons, the errors, I'm sorry, through my convolutional layer. So I will have here, there will be some error delta. If this is some layer L, and this is its item ij, then it will be back projected using a particular weight of that connects this error to the neuron of the preceding layer. This is a preceding layer, and I'm accumulating in a convolutional layer. I'm accumulating layer also using a backpropagation algorithm, but this time my connections are local. So that will be just only difference in computing errors that are performed, that are made at any neuron in my structure. It is always a result of projections, and I can do that. So the first layer, the output layer of my fully connected part module of my cellular of my convolutional neural network gets these errors. gets these errors. So these errors that are a result of computing a derivative of a softmax. And these errors are very simple, as you see. And all the remaining procedure of projecting involves okay, I will respond to it. There is a question. I'm sorry, I'm reacting with a huge delay for any question. I will respond it in a while. But just to conclude this part, is that the conclusion is that I can identify, let's say, errors for each neuron in my CNN are identified via backpropagation algorithm. And in the errors at the last layer of MLP, it's just either 1 minus delta I. This is for so it's not I'm 1 minus QI, not delta I, for the output I, or QJ for all ij different than I. So that's that's the input to this backpropagation procedure. And softmax provides us with a very simple form of this input. If we choose any other way of normalizing or converting outputs of a multiple layer perceptron, this dense part, of converting these values onto probabilities, as I said, we can do it in any other way, but none of the ways will get us such a simple results. So that's why softmax has been adopted. And now I have a question related once again. What is the difference here between these two? I have here two different formulas. What I have observed that the loss that I have, once again, is a minus logarithm QI. So this is the loss at the output of my whole network. And this will be something that I will be projecting back. And I will be projecting this back in many, basically in all paths in my network. So if this is my last, this is my last layer of my multiple layer perceptron of this dense module. So this is dense module. So this is this dense part of a module. And here I have this softmax, and here I have a loss. So what I need to do is I need to project this back. This loss needs to be projected everywhere. For every path in my network, it needs to be projected. So it needs to be projected here and here and here. All the lines, I will need to project this loss because I'm computing these derivatives, dl over every parameter of my network. So I need to make projections. And if my winner is I, that means that basically I'm interested in this probability. But this probability QI, let's move it here. this probability Qi is a result of applying a softmax for all outputs of my preceding layer. So I am applying the softmax to all outputs from 1 through p. So this is the output number 1, and this is the output number p, and somewhere here is output number I. But as you see, this Qi is a function, some function f1 of yi, but it is also some function, let's say f2, of yj, any other output. Just in the denominator of this expression, you see that output I depends on any output of the preceding layer. So what I need to do is I need to compute a derivative of Qi, both with respect to yi and with respect to yj. And these are different derivatives. So is it clear? Is this explanation understandable? Benjamin? Yes, okay. I hope when you just have a chance of looking at this for a while, it will become absolutely clear. I will be propagating my error or my loss to the left, and the first part of my propagation is how to propagate it through a softmax. And this propagation through a softmax basically has two different ways. The first way is if I am propagating my probability I with respect or in a direction to my input I, then I have a different function that I'm differentiating. But if I would like to propagate it towards some other output, yj, then the function does not, the loss needs to be differentiated only with respect to this yj. And differentiation with respect to yj, it does not include this component yi. So it is different. Anyway, these are not very trivial ideas, but they just require a little amount of thought, and I'm sure you will get it, because once again, what we are talking about a very complex structure. So now, once again, this structure is a structure where I have several modules. So I have my input, and this input can be either two-dimensional, but it can be RGB, then it will be three-dimensional. So data from this input is processed by my first convolutional block, and then probably it is transformed, or maybe within this block I can also have this nonlinearity. And then what I can do is I can do pooling, and if I do pooling, I'm reducing size of my data, and I start with another set of convolutional filters, or there will be another convolutional block, and so forth, until we get to this flattening layer. So this is my convolutional part of a network, and a result of this is my representation. This is my representation that is input to MLP. This is a MLP, or dense or fully connected part of my network. So it could be just a single layer, it could be 2, it could be 3, it could be 100. And at the end of this, I will add here a softmax, just to convert it to probabilities. And now I have a probability vector at the end. And if I would like to learn how to change parameters, so I will have parameters here, some parameters of my first convolutional layer. Here will be a parameter of my second convolutional layer, and here will be parameter of my last layer of my fully connected network. To compute these values, what I have to do is I have to use this delta rule, basically. But delta rule requires me to identify the error. And the error is something that I'm back projecting. And I'm back projecting this error in a very homogeneous way. So I am looking what are the errors at the outputs of this layer, and I'm multiplying these errors accordingly so that I can project them onto the neuron that I'm interested in a weight. I'm interested in a weight of a particular neuron. And this is a very, very systematic procedure. And this systematic procedure is extremely important, because it gives us a simple algorithmic way of training very, very complex structures. Because how many layers I might have in my convolutional neural network? I can have as few as 4 or 5 layers. It happens, but I can have 1,000 layers as well. There are different architectures that, especially that the differences might concern this fully connected module. There are some concepts we will not have time for introducing them. But there is a concept of something that is called a residual neural network. And this is a concept where I can place here hundreds of fully connected layers. Also, these convolutional layers, there can be many of them. And many of them, how many I will be using is partly determined by a size of input information, because I would like to have a chance of performing the analysis at different levels of resolution, also to be able to combine at a very coarse level of resolution. So if my input is large, I will need several poolings to get to such a high level of generality in my analysis. But the most important thing is this weight learning. And this weight learning, once again, if I would like to make a correction of the weight that is in some module, doesn't matter which, and let's say this is a alpha weight, it is some neuron's weight. I will always use this delta rule, and this delta rule will include this projected error, and it will include all the information that are at the input of this neuron. So if I have any neuron and I will have some weight that I'm interested in, this is a parameter that I'm interested in. So what I need to have this projected error. What I need to have, I will need to have a derivative of activation of this neuron, and I need to have what is at the input. So basically here what I have is f prime sub s times x. And this is and this is how this delta rule looks like. Yeah, I'm repeating this several times, but this is essential. That's why I would like you to have a feeling that this is a very important thing. And my delta, which is back projected, this back projected delta basically is always a result of projecting deltas from some next layer or +1 layer. And in projections, what I have is I have again derivatives of neurons that are in this +1 layer, and weights that connect my neuron with all of these neurons. So this is over J, so there will be some J, and here will be some J here, and there will be some J here. And if my neuron is this neuron related to a neuron alpha, so that I could write this like this. And why I am again introducing this formula. This time I'm introducing this formula to show you that we are having a problem that emerges if we would like to build convolutional neural networks out of neurons that we are considering so far. So what was the neuron that we are considering so far? The neuron was an algorithm or a device for converting input to output. So there was a dot product, and I was converting this into the output. So these were the neurons. And the second thing that I assumed as so this is a state. This is a state. The second thing that I was assuming so far was that I have a sigmoid nonlinearity. So this sigmoid linearity, most often it was a logistic function, and it was something that matches biology. That was something that is very close to what biology does. But if you look at the formula for weight update, and if you recall that we are talking about multiple layer structures, it means that the error that I am computing here is the error that is being projected from the previous layer, and the error from the previous layer is projecting from its predecessor, and so forth. So there will be several layers of projecting errors. So if we start from this last layer of my fully connected network, there are some errors here, and these errors get projected to m-1. So there will be errors delta, let's say with a superscript -2, and there will be so forth. There will be the first layer, there will be an error -m, and so forth. Now we have these convolutional layers. Also, we are back projecting errors. So if I have many layers, let's say I have 10 layers, then I will be repeating this 10 times. And every computation of my error involves multiplication by a derivative of activation function. So now, what's the problem? Where is the problem? The problem is that a derivative of the activation function, if this is a logistic function, is just y times 1 minus y. And if you look, this is a monotonous function. So if I have a sigmoid, again, this is my sigmoid. So this is f. So my derivative is something that you see that here the function saturates. If it saturates, that means a derivative gets 0. And only region where I have non-zero derivatives, so this is with respect to S. Everything is with respect to S. So the only region where my derivatives are positive are in this central region. And basically, if you would like to see what's the maximum here value for this basic sigmoid, it's 1 over value is for here is in at this point I have 1 over 2. That's a value. So a derivative is 1 over 2 times 1 over 2 equals 1 over 4. That's the maximum value for a derivative. And if you look at this expression, this is just a number. And even if I am operating in this central region, all neurons are operating in this central region, which is unlikely, then I will have somewhere, if I'm computing an error in some layer that is close to the front of my network. So this is somewhere at the beginning. Then I will have a lot of products of values that are, let's say, these two neurons were operating near the center of this domain. So a state was around 0, but most of them probably had some more definite states, more decisive outputs. So probably there was 1 over 1 in some neuron, and some other neuron had 1 even less, and so forth. So as you see, a presence of this derivative of activation function, the presence of this derivative activation function makes or dumps values of this error, makes them 0. They tend to 0, and this problem was not fully obvious and evident when I was talking about this 3-layer or 2-layer multiple perceptrons or 2 or 3-layer networks. But if these networks begin to be deeper, if they start to have more layers, then we have a phenomenon that is called a vanishing gradients. Because these gradients, this error basically is a gradient of the or a derivative of loss with respect to a particular output of a neuron. And it vanishes because it involves product of derivatives. And most of these derivatives, for all the neurons that are already kind of better trained, that means that they know how to respond and they produce some firm decisions. So, oh, this is 1 or this is 0. This activation tells me I recognize it, and this is 1. That means that the derivative is close to 0. And if it is close to 0 when multiplied, means that if I am passing my error to the preceding layer, then it gets attenuated, it gets damped, reduced, and this reduction is multiplicative. So if I go 1 layer further, I will increase in an exponential way this phenomenon, this drop. So how could we cope with these vanishing gradients? How to solve this problem? Because these convolutional neural networks, they appeared just not to learn. It was impossible to train such a network just because information on errors was not reaching these first convolutional layers. They just had no information about an error. It was so small that the training was ineffective. So what can we do, and what has been done? Let's give up this biologically plausible nonlinearity. This is something that is not going to work well for deep structures. Instead, what has been proposed is a different layer, different proposal or concept of nonlinearity. Like, what is the most commonly used nonlinearity at this point in neural network? You for sure you know, because you already found this name, and this nonlinearity is a piecewise function, and this function is in this region. This function is y equals s, and this region is y equals 0. Or I can say that y can be defined as the maximum of 0 and s, and this function is called rectified linear unit, or ReLU. So this is a rectified linear unit, and this is the most commonly used nonlinearity in deep neural networks, just because they provide a gradient that is constant, because a derivative of this function f prime with respect to s, if s is non-negative, a derivative is a constant value, for example 1. So there is no adverse effect of reducing information on error during backpropagation. As you see, if only in this pipeline of projection we have neurons with negative state, then this path will disappear with this path, and this is one of the troubles with deep neural networks, that there are many neurons that basically do not contribute to learning, just because they are on these paths where when I'm trying to backpropagate an error, they contribute with multiplying this by 0. And because of that, there are several other concepts on how to improve this neurons nonlinearities, so that on the one way we don't have this phenomenon of vanishing gradients, and on the other way we do not have zeros if the derivative is non-zero, if activation is negative. And probably one of the most commonly used solutions to this is something that is called a leaky ReLU, which is just a function that is very similar to the one. So here in this part we have y equals s, but here we have also a small constant gradient. So this is something like, and again, there is no any better multiplier than, or maybe there is no any good way to identify this multiplier, but commonly it is 0.01. So it is 100 times smaller derivative, but it is non-zero. But this ReLU seems to be a standard right now. So this is something that is commonly used in practical implementation of all neural networks. There are many other concepts on what could be a nonlinearity. And there are very interesting concepts, very interesting ideas, but they do not provide, I think, any qualitative advantage over ReLU. ReLU is something that works so far well, and all the other proposals are not qualitatively better. They in some tasks they appear to be better, but in other tasks not necessarily. And since ReLU is so simple and computations are so effective, most of people and most of models assume this ReLU as its basic default solution. And there is one more thing that I would like to mention. So what we have covered so far, we covered so far most of the elements of this convolutional neural network. What we covered these convolutional modules. Then there are these pooling layers that reduce resolution. These pooling layers, as I mentioned, are not mandatory, because I can play with stride and also get a reduction in resolution. One more thing, because I forgot. If I have a pooling layer, when I am propagating errors, so the pooling layer is basically, I take 4 different, if this is a 2x2 pooling, I'm taking 4 inputs and I produce 1 output. Now, what about error backpropagation? So if I have an error that has been projected to the output of this pooling layer, what will be projected back? So again, the solution that has been adopted is very simple. It is just exactly the same value. So I am, if I am projecting delta at the output of pooling of a pooling layer, it just gets appropriately regenerated for every. It is replicated for every input that is producing this output. It's just a replica of what comes to the output. So we have convolutional layers, we have pooling layers, and again, here is this multiple layer perceptron, and then there is the softmax, and this is the output of my convolutional network, which is a probability vector. One more thing is that we have addressed this problem when we were talking about machine learning. The problem is that if I have a typical classifier, you have already made some classification during your labs. And one of the things that you probably noticed was what was the complexity of your network. And complexity of a network is huge. Complexity, which is a number of parameters, is at the order of millions and more. Maybe for some simple tasks, what you can get are just hundreds or dozens of thousands, but typically it will be millions and more. And how many examples can you provide to train this structure? Well, it is not that easy to collect sufficient amount of examples, because always the learning always is some statistical procedure. We are looking for regularities. That's the essence of learning. If something repeats, then it means that this is a rule. And if something repeats, I will get consistent changes in weights. And this is how I learn. I learn by observing regularities. But if I need to observe regularities, I need to have sufficient amount of examples. And we were talking about this problem on machine learning. If I have too few examples with respect to a number of parameters that I would like to calculate, then I won't be able to learn anything, because there are infinite amount of parameter sets that can match my observations. And most of them, or majority, or vast majority of them, will be wrong combinations of parameters. So this is the effect is known as this memorizing examples, which is not maybe the most accurate way of expressing this phenomenon, but this is a handy way of saying that my network haven't learned anything; it just memorized training examples, and this is because we don't have enough data to train correctly all the parameters. So what are the ways to mitigate this problem? The first way that we are talking about during machine learning was regularization. And in deep neural networks, this is obviously one of the solutions. So we can regularize weights of maybe of a specific layer, or maybe of many layers, or of all layers, and we can regularize using either L1 or L2 regularization. And every tool that is designed for simulating deep neural networks offers this option. So you can always apply regularization, and without regularization, if you have too many parameters with respect to a number of input data examples, don't expect you can learn anything. But there is another concept, another idea that is implemented and that actually works, seems to work even better. It is called a dropout. What is a dropout? A dropout, again, is an extremely simple concept. So if I have a layer, it can be either a convolutional layer, or it can be just an MLP layer. A dropout is a mechanism. So if I have neurons in a convolutional layer, or if I have neurons in this multiple layer perceptor, and this is some filter I, and next to it there will be a filter J, and next to it filter K, and here are just multiple layer units. So in a standard way, all neurons participate in learning, and all neurons participate in processing input information. And one of the explanations for this memorization problem is that we might find neurons that by chance are quite well matching a particular example. By chance, they have a very similar weights, so that if I see some particular example, this neuron becomes active, and all the remaining part of the structure is taking into account the response of this neuron and is adapting to a response of this neuron. So there is a path that forms, and this path is kind of specialized for a very particular example. And if I see this example, this neuron always gets an increase in weights, and it specializes in representing this particular example. And I can get a very good results of training if I have a structure that has huge number of parameters, few examples, just because there will always be by chance many neurons that respond well to input examples. And after learning, what I will have that on this training set, I will have a very, very high performance, but this is because there is a neuron or a set of neurons that are just matching this particular example, and they are producing high values of a dot product. So I have a very definite responses, and but if I then try to run my network on examples that has never been seen, so since such an example does not fit this neuron, dot products will be much smaller, and probably the network will not operate at all on a test data. And the idea is that I can try to break this specialization by random elimination of different neurons in different stages of training. So if I have online training, so if I have online training, that means that I'm providing an example and its expected output vector, and I am computing a loss, and I am back projecting a loss. So if this is example, let's say 1, I have some loss 1, and I will have some updates. Without the dropout mechanism, this is something that will cause that some neuron that fits well to this example will get amplified its weights to detect this particular example. But now a dropout is just probabilistic or random elimination of neurons in different stages of learning. So in the first stage of learning, for example, this neuron was present, but in this phase of learning, I excluded these neurons. They were just excluded from a network. So I'm not training these neurons. They do not take part in data processing. So there is a forward pass. Also, they don't participate in a forward pass. And this is in time instant 1. But now there is the second sample, or the later, the some other time. We have a, let's say, again the same sample after some time, because we will be training in epochs, so it would produce exactly the same updates, but what I can do is I can eliminate. Let's make it black. Make it black again. So this time that was this neuron, but now I will eliminate it. In this, I will make a completely random, different choice of neurons that are excluded. So my So this time, these are the units that take part in both forward pass and in update. So we are forcing a network to not to memorize examples, because now other neurons will learn something that is important for this particular example. So this is this time instant, some time instant 1, this is some time instant 2, but now I'm not using this neuron. I'm not retraining this particular unit. And dropout is something, it's introduced as a layer, as a kind of a layer of switches. So if I have in MLP, in this fully connected networks, what I can say that if I have this layer I, this layer I will be preceded with a dropout I, which is a kind of a set of binary values, like randomly generated binary values, that will just select whether some particular neuron is active or not. So if this is 0, these neurons will not be active. All the remaining ones will be active. So here these are active. So this is a way of handling a problem of lack of data. So basically, we are done with convolutional neural networks. And during a lab, probably you will still play with building convolutional neural networks, training them to perform classification tasks, data classification tasks, because they were introduced. So the CNNs, were introduced as a means for basically image classification, and image classification was the first successful. It's more than successful. It was a breakthrough of the concept of deep learning. So image classification was the first application that showed that neural networks have a huge potential in solving difficult problems, real-world problems, and they evolved. Deep neural networks evolved, obviously, beyond image classification. And we don't have more time. So I will just briefly tell you what else is available. So the first idea was, if I am having images, let's build and let's make it, this is a CNN. Let's build the algorithm for data classification that will indicate with labels what is present in input. So there will be something like in recognizing people. This is Joe, for example. And that was the beginning, when people realized that all these new ideas that has been added to neural networks, and these new ideas, they involve representation learning, because the most important word is that in this deep learning, the word deep, it refers not, it basically does not refer to the fact that we will be having several layers, but this is also the case. So that's the first obvious, the obvious property of these models. We have several layers, but the most important seems to be that we are learning a representation, that we have a way of coming out with better representations of data. So deep learning extended conventional neural networks, and because typically we are dealing with deep neural networks. The concepts, the other concepts also benefited from this, and we have also deep learning applied not to neural networks, but predominantly we'll be talking about deep neural networks. And these novelties were let's learn representation. That's the first thing that is very important. The second is that if we would like to classify, it's probably better to use a different evaluation for this classification, a loss function, a different loss function. So let's go with cross entropy or categorical cross entropy instead of mean squared error. Mean squared error is still used when we are doing regression, because for regression, mean squared error is still the most reasonable way to use. And all the other concepts are like let's change nonlinearity of a neuron, so that we are avoiding these vanishing gradients, so that we can train effectively a structure. Let's introduce dropout as a means that supports regularization in handling insufficient amount of data. So there are many new ideas that after introduction enabled a leap, a huge advance in performance of intelligent data analysis, of dealing with real data. But obviously, not only image classification tasks benefited from this deep learning. Observe that CNN, basically one of the basic properties of CNN is that it is a feed-forward concept. That means information flows in one direction, and this is something that is okay for doing regression or doing object classification. It is okay for anything that does not have to rely on a history of some process to make a good decision. Because if I start to rely on a history, then I should provide some mechanism of modeling a sequence, of modeling temporal relations or ordering relations among data. So if I would like to solve other types of problems, I need to introduce feedback. So my data flow will no more be one directional, but there will be some input. There will be some input vectors that I will be introducing to my structure. And in my structure, I will be obviously producing some output based on this input data. But also what I would like to, for example, do is to use previous outputs. So let's assume that these are many neurons. These are some modules of neurons. And this is, again, some module of neurons. So if I propose this architecture is qualitatively different from the previous one, because this architecture involves feedback. That means I will produce output not only based on input, but also based on let's assume, I call it a state or memorized information. This is not the neuron state. It is a state of the whole system. And depending on, and I can train this. basically networks, neural networks that are that involve this feedback are called recurrent neural networks. Recurrent neural networks, and they get trained in a way that is that is an adaptation of backpropagation algorithm. So you might find an abbreviation BPTT, which is the algorithm for training such networks, and the algorithm name is backpropagation through time. So this is what you can do. You can train neural networks that are that include feedback. You can train recurrent neural networks, and these recurrent neural networks are able to base decisions on previous history of input sequence. Now I'm producing a sequence. I'm processing a sequence. So I have a sequence of objects, of events, and this is something that I am passing to this recurrent neural network. And as a result, I might have either this network might classify. So I can do different things. I can just classify something. But this classification now it's more complex because it involves history. It's not just based on a structure of what I see. But also I can transform sequences. I can transform accordingly sequences. So transformation of a sequence, for example, is I get the input in English and I produce the output in Polish. So I can do translation. And this is one of the extremely researched domain because it's extremely useful. So this natural language processing or language translation or all this can be done using these recurrent neural networks. There are some modifications of these recurrent neural networks that there is a whole family of different methods, and maybe you have heard about LSTM, not LTSM, but LSTM. This means long short-term memory and many other variants that are operational and that do things that are impressive. So just at the end, just let me mention also some other applications and architectures of deep neural networks. So what I mentioned already is that neural networks can be used for processing or transforming sequences of events or sequences of data. But also neural networks can be used to generate new contents. You are all aware of existence of deep fakes, where we are generating images of non-existent people and they look realistically. And we are also able to generate videos of non-existing scenes. We can generate speech, and it is becoming also extremely realistic. So we have generative models. There are many generative models that has been proposed, and this is a extremely broad again and extremely interesting area of research and dynamic area of research. Maybe you have heard about an acronym GAN, which stands for Generative Adversarial Networks. adversarial networks that are extremely successful in generating, for example, images, but also in generating speech. There are also, and obviously this is not the only one approach. There are other concepts that can enable you to produce contents that is amazingly realistic of different kinds. We have something that is called normalizing flows, and we have something that is called autoencoders or variational autoencoders, and so forth. So here again, we have a huge amount of deep approaches to generate new contents. And one of the last thing is we have something that introduces, in using these deep concepts, something that is called the reinforcement learning. So there is a deep reinforcement learning, and probably you have seen spectacular examples of different multi-pod robots, or hexapods, or animal-like quadrileg or quadripod systems that where the control over this motor functions of such robots is basically learned using deep reinforcement learning. So there is a lot of applications, a lot of other concepts, and this is a good moment in time of your education, because you are free to choose one of these exciting fields for your future careers. And there is a lot of offer right now everywhere in the world. People or experts or people who are willing to learn machine learning are sought, and these are really interesting and ideas, concepts, and I hope you will be able to, if you are interested in that, I'm sure you will be easily able to build your future career around these problems. So we will meet only once again for a test, and I would like to stop at this particular point. And I wonder whether you have any questions related to the course, related to the field, and I'd like to thank you for attending the course. You'll still have lab work. The test, I probably will ask you to analyze what happens if I am as providing some input data, some sample, some training sample, which is composed of input vector and a target vector, to a structure that is composed maybe of a convolutional layer, like 3-element convolutional layer, and maybe one layer of a regular dense network. And I would like to ask you to tell me what will be the output for that sample. And I would like you to tell me what will be updates of parameters of this network. So this will be something very, very practical. I will show you the architecture. very simple, because this is something that you need to be able to quickly do with your pen and a sheet of paper. So it will be a very simple architecture. And this will be an architecture that is a miniature of a convolutional neural network. And I will ask you to tell me what will be the output of this network if I provide you with some input, and what will be updates of parameters if for such a network. Yes, in terms of the last question is about literature and information about GANs and reinforcement learning. So GANs, during the last lab, my colleague will introduce you to GANs, and he is extremely so just to conclude the last question, this will be just a single question. This will be just a single assignment, single task. And coming back to GANs, he will be able to give you a lot. There are a lot of resources on GANs, I actually you are ready to learn GANs. So there are no there are slight modifications of the concepts that you know. For example, in GANs, what you will have something like that is called inverse convolution layer. But you are ready to be able to grasp what is the idea. And also reinforcement learning. There are for reinforcement learning. Before you go to deep reinforcement learning, probably it's a good thing to learn classical methods as well. And I guess that I think that the name of a person who wrote an excellent book on reinforcement learning, and maybe including deep reinforcement learning, the author is Sutton. And probably DeepMind is something that is working actively, and it offers a lot of instructional materials on reinforcement learning and deep reinforcement learning. On GANs, the amount of information on GANs is huge. And if you ask Dr. Kapusta, who is working with these GANs for a few years right now, he will for sure propose you some short list of must-read paper. Okay, so and if you are interested in writing maybe your master thesis in reinforcement learning, a colleague who is working with this is a colleague from our institute, is called Dr. Piotr Duch. So if you are interested in reinforcement learning and extending your knowledge in this direction, I recommend him. For GANs, Dr. Paweł Kapusta is the right person to contact. Okay, so that's it. Yeah. Any other questions? Obviously, if you have any questions and you would like to ask them, and there is no time right now, just write me an email, and in my spare time, I'll try to get back to you. Okay, so Thank you. I'm I'm very glad to hear that, and thanks a lot. I'm very glad, and thank you for appreciation. And that's probably mostly it is it is. It is because of your capacity and of your involvement that you are the person that is an author of this success. That was just. I hope it was handy. There is a huge competition because you can find excellent courses online, and I think it is quite easy right now to learn deep learning and machine learning, because there is an extremely, this is extremely important. People are extremely competent in many different places, many different countries. You can find someone who is an expert. And I'm pretty sure, yeah, and this is a good direction in terms of future career. What I'm receiving weekly at least 10 or more PhD offers from different universities around Europe or around the world, and also postdoc offers. It is extremely hot domain right now. So I think that right now I think this direction is one of the best ideas, and it guarantees you that you will have work, extremely interesting work, because you are solving problems that are tough, that are important, that are useful. So I wish you a good luck. Regarding the question on the test, I think you will. I will give you both pass through and back propagation. So back propagation, it's just recall that there are a few phases of this back propagation. The first back propagation phase is a back propagation through a softmax. And then you have a conventional back propagation in multiple layer perceptron. And then you have back propagation through your convolutional layer. And you are projecting errors back exactly the same as in fully connected network. The only difference is that if you want to make an update of a weight, you need to remember that all the weights in input convolutional layers are the same. Every neuron has the same set of weights. So this is something that that you have to keep in mind. That you will have a lot of time. There will be 2 hours, so you will be able to think, to use all the materials that you have, obviously, and I don't think there will be any problem. And I hope you will be satisfied that you can solve a problem that is not trivial. I need to. I will send you. Please send me an email, and I will send you some sample question, sample like assignment, so that you can know what to expect. Okay, so I guess we soon will be expelled from this room. I wish you a good luck on all the remaining exams, and basically good luck and all the best in life. Stay healthy, take vaccines if you haven't taken so far, so that you can live normal lives. And all the best to all of you, and and uh, and have a great summer also. Thank you. Bye bye.